Hi everyone, my name is Tejas Chopra, and today I'll be talking about compacting small objects in cloud for a high yield. The agenda for my talk is as follows. I'll go with a brief introduction and speak about myself, the problem statement, and what we were trying to achieve, some basics about what compaction means, data structures that we introduced, such as blobs and blob tables, file system operations that we had to modify, and finally, some results and takeaways. I'm a senior software engineer at Netflix. I work with the data storage platform team here at Netflix. My job is to architect the backend infrastructure to support Netflix studios and streaming platforms, so managing exabytes of data and billions of assets. I am also a keynote speaker on distributed systems, cloud, and blockchain. Prior to Netflix, I was a senior software engineer at Box, and before that, I worked at companies such as Datrium, Samsung, Cadence, and Tensilica. So companies nowadays are moving a lot towards cloud, where cloud provides object stores for these companies. The cloud footprint for many of these enterprises is exponentially growing. Uh, when you think about cloud file systems, a simple way to think about it is each file in your local system will map to an object in cloud. Um, However, from experiments and research, it is seen that a lot of the cloud workloads in today's world contain many small files and are bursty in nature. Just like random writes are not suitable for file systems, in the same way, small sized files are not beneficial for cloud storage. And that is primarily because of two reasons. One is the request level cost, and second is throttling. So when it comes to request level cost, you pay a cost to actually do puts to the cloud. So to upload a gigabyte file with 4 kilobyte puts is 57 times the cost of actually storing that file on cloud. And with regards to throttling as well, Amazon S3, the best practice guideline says that if you have more than 300 puts, deletes, or lists per second, or more than 800 gets per second, S3 will rate limit. So what that means is a 4 megabyte put is 1000 times faster than 1000 4 kilobyte puts. And you can see here that as the object size on the cloud increases, the average throughput also increases. This was the basis for our research and compacting these objects. We talk about S3, but there are a bunch of alternatives other than S3 to store files and folders on cloud. If we talk about the Elastic file system, it is a generic file system and it only charges for storage, so no put or get request costs. The cost is around 0.3 per gigabyte per month. DynamoDB, which is a NoSQL database, charges you for storage and for the amount of writes and reads you perform. So it is 0.25 per gigabyte per month for one write per second per month, and 0.09 per gigabyte per month for one read per second per month. S3, as you can see, has very little storage cost, which is 0.023 per gigabyte per month, but it has a cost per put. So if we have to compare these different systems, to store 1 terabyte worth of 4 kilobyte files and each having workloads that perform hundreds of writes per second, as is if we use S3, it will cost around $1,366 per month. One thing to note is that the operation cost, which is the cost of puts and gets, is like 98% of the total cost. So it takes 5 years of storage to match this operation cost. In Elastic File Systems, it is $307. The operation cost is zero because it doesn't charge for puts or gets. DynamoDB is $303 and the operation cost is 16% because it actually includes that in the costing of its storage as well. And it takes 5 days of storage to match the operation cost. With our solution, with compaction, the S3 cost will be brought down from $1,366 to $24, and the operation cost would be just 0.001%. So it will take 27 seconds of storage to match the operation cost. What exactly is compaction? Compaction is nothing but a pluggable module on the client side, which will pack the data, the small files that you want to upload to cloud, into gigabyte-sized blobs, and also maintain an index of where the file is within the blob. There are two types of indexes that we maintain. One is within each blob, there will be a footer that contains the index of all the files in the blob. And second is a redundant global index of all files in all blobs that is maintained on the client side. And this is for both fault tolerance and also just to have a backup. Uh, Coming to data structures, there are two types of data structures that we employed. A blob is a single immutable object on cloud. Data from multiple files gets packed into a blob, and the footer of the blob, like I explained, contains information about the byte ranges of the file within the blob. By reading all the footers of all the compacted blobs, we can recreate the world. We could have used SS tables that is used in many places, but it requires some form of sorting before persistence. The second data structure is the blob table. Uh, it actually provides an optimization over reading all the blob footers. It's just a global database, a global table that contains information of all the files and where they are present in all the blobs. It can be recreated, so it's redundant. And consistency of a blob table is a challenge because blob creation happens on different machines and is distributed in nature. Uh, in order to compact, you need to have sufficient data to be accumulated before it is compacted. And the data is buffered on client nodes, and it is not considered durable until it is pushed to cloud. So you have an intermediate state where the data is just being buffered for compaction, and it's not yet made it to cloud. So all the policies, all the lifecycle management needs to take that into account, and SLAs as well. Um, so compaction policy is specified at mount time. Once the data has been compacted, the embedded indices within the blob get updated. Also, when we store the blob on the cloud, we give it a unique name. We give it the IP of the client that has generated the blob, the offset of the footer within the blob, and the date at which it has been persisted. And this will be used once we read the blob to exactly know where the footer starts so that we can populate our blob table. That's why we put the footer offset within the name of the blob itself. After the blob has been pushed to cloud, the blob table gets updated with new extents for the file. So in short, the global blob table always maintains the updated location for each file. If the file is buffered on the worker, it contains the worker's IP. If the file is a blob on the cloud, it contains the blob's object ID and the file's extent in the blob. There are a lot of changes that are needed in reads and writes and other operations, and we'll get into that now. So when you read the data, when a read request comes for the data, where do you find the data? It really depends on where the data is present. The data could be buffered on the client, or it could be pushed to cloud already in the form of a blob. The blob table contains the location of the data. So if a client has the data, what you can do is you can perform worker to worker transfer for reads. And if the blob is present on cloud, you can actually read the range. There is a range read request that many of these cloud providers provide. So you can read a particular range from within the cloud blob. Uh, but you may also want to fetch a little more than what is needed because that is the essence of prefetching and will give you performance benefits. Uh, when it comes to deletes and renames, uh, when a client issues a delete for a file, you remove the entry from the blob table. And that's it, the delete is complete. But over a period of time, each blob may have many of these deleted files within it. So what we want to also maintain is the liveness of a blob. How many files within the blob or how many extents within the blob are active right now. If live files are less than a threshold, we would like to repack the blob. So what we do is we have a worker on the background, which will actually look at the liveness for each of these blobs and then repack these blobs into newer blobs and then update the blob tables appropriately. Renames. So renames are also tricky because what you want to do is rename should be an atomic update of the file's name in the blob table. So what you do is you piggyback on the future blobs embedded indices to issue these renames. For recovery from embedded indices, blobs are read in the order of creation. So the latest blobs will always contain the rename information. Um, Coming back to fault tolerance, because our system relies very heavily on the client that buffers a lot of the data before sending it to cloud, what we need to take into account is what happens when one of these client workers dies or what happens when the master dies. So for the master, we maintain the global blob table in the master, and we periodically back it up to cloud as well. On a crash, we read the last checkpointed blob table and then follow it up with all the embedded indices within each of the blobs that were written after that time. So that way you can actually, when you start up, you can recreate the world by doing a combination of the blob table and the embedded indices and blobs. On the client side, files that were buffered for compaction are lost because they haven't yet made it to cloud, but they can still be recovered if they have been persisted on the local disk. If the files have been compacted and pushed to cloud, blob table contains all the necessary information for recovery. If it has been compacted and pushed to cloud, but the blob table is not updated, the embedded indices contain the information for recovery. And these are the results that we got after employing these changes. So if you look at the price comparison and the throughput comparison, we see that without packing in terms of cents, when we were writing 24.4 gigabytes worth of 8 KB files to Amazon S3, we saw a 25,000x improvement in price. And in terms of throughput as well, we saw a 60x improvement in throughput by just employing compaction on the client side. And finally, to conclude, cloud file systems should aggressively compact small objects. There are significant costs for both operations as well as there's a lot of rate limiting. By just employing compaction techniques, we were able to improve our throughput by 60x and the costs reduced by 25,000x. This becomes especially important in enterprises such as Netflix, where you have bunch of these small objects and small files being created. Uh, the other use case that we've thought of for this is backup of smaller files, because when you back up these smaller files, they can be archived using this strategy to improve both backup times and costs. And compaction policies that actually collect the data to compact, we can select it based on create time when the files have been created. Similar files that belong to the same application can be compacted together. And we also plan to apply some form of machine learning to choose the objects to compact together. Objects that have a similar read profile can also benefit from prefetching that is done during the entire blob creation. So with that, I would like to conclude my talk. Please feel free to reach out to me on my email and Twitter. And if you're looking for opportunities in Netflix and if you're based in the US, please feel free to reach out to me. We are looking for distributed systems engineers, file systems engineers, and folks that are interested in cloud. Thank you.